because in fact, small groups just mean that greater opportunity for discussion, interactivity. I teach way too many courses with 80 people, 200 people. I do like kind of having these smaller discussions. So since we're a smaller group, please feel emboldened to jump in anytime with comments or questions. I'm opening up the window so I can see people with your raised hands. I've got the Q&A window open. I'll have the chat window open. I have everything open. Okay, thank you very much to everybody who's joined in today. What we're going to do is we'll talk basics, fundamentals, probabilities. We're going to talk about frequentist and Bayesian probability. We'll put them together, and then discuss the simplest machine learning methodology of all from the frequentist and the Bayesian perspective. So that's it. That's what we're going to do today. I think this is a wonderful opportunity to go back to fundamentals. And I'll tell you, we still need the fundamentals. They're very powerful. Everything we do is built upon probability. Okay, so I'll have an introduction of myself. I promise just a couple of slides of bragging, and then I'm done. Probability. And then we'll talk about linear regression in frequentist and Bayesian perspectives, and do a demonstration in Python of both. So that's what we've got to plan. The introduction, I'll be very quick about this. I think I recognize a lot of the names. If there's anybody here that has never taken a class with me or worked with me before, it's pronounced Pyrcz. If you say it like that, that's as well as I say it. I've met Ukrainians, and I think we lost the ability to say our last name during 100 years in Canada. I'm from industry. I did spend about 13 years in Chevron's energy technology company. Many things that I teach, I applied. I did in practice. I've only been a professor for about 3 years now. And so I do have experience in application. I'm very flexible. If anybody has ideas or something else they want to hear about, well, we'll make a little webinar on it. We'll add content. We add content all the time. Avi knows we work together and make a lot of new content. I do have an open door policy, and I do have many people contacting me, and I'm happy to discuss as much as I'm able to, get back to people. I'm an engineer and a geoscientist. If I explain something from an engineering perspective and you're a geoscientist, let me know and I can switch. I can start using that geoscience voice in my head. That sounds a bit different at times, uses different terminology, but I can go back and forth. I'm bilingual. I frequently teach and consult in our industry in the subsurface energy, mining, water, and so forth. And I see what's being done within the industry. And so I can tie what's being taught here to practice. And then finally, besides datum, I do a lot. Anybody here on Twitter? Anyone on Twitter? I'm trying to look at the names and see if I recognize someone from Twitter. Okay. Anybody ever check out the YouTube lectures, the GitHub, and so forth? I do share a lot of educational content, open educational content, in addition to all this efforts with datum. Okay. What's the goal today? I promise no more bragging. I'm not going to say anything else about myself the whole day. And I apologize. That was too much. Teach you theory and application so you can use it immediately to add value. Frequentist probability, Bayesian probability. Maybe you'll come out of this as you were a frequentist and now you'll be a Bayesian statistician or a Bayesian practitioner. Or maybe you were a Bayesian and you'll start to appreciate and understand the contributions from the frequentist approach. We'll present the world's simplest machine learning methodology, frequentist and Bayesian perspectives for linear regression. And the whole idea is to strengthen your machine learning knowledge with a foundation in probability. It all comes from, no matter what you do, it comes from probability. Okay, why cover probability and basics of statistics for machine learning? I do appreciate, anybody here like the book James and All? Hasty and All, the other one? The book where the term is statistical learning. They don't say machine learning, they say statistical learning. Right in the title. I agree with that. I think machine learning is statistical learning, and I do use the terms interchangeably with my students to promote the idea that it is all based on statistics. So that's why we want to cover basics and statistics and probability. Machine learning methods to make predictions based on, if you think about it, you're using sample data. Well, as soon as you're using sample data within your training and testing data sets, you invoke a lot of statistics as far as representativity and sampling, the number of samples, uncertainty due to sparse sampling, bootstrap, and so forth. Don't even get me started. As soon as I start talking about uncertainty in the sample set and I say bootstrap, there are going to be people here who are starting to think about bagging. That's a machine learning methodology by which you use multiple realizations of the data set. These are all fundamental statistical concepts. Summarizations in statistics, the model parameters are often based directly on statistics. Anybody ever built a decision tree? The decision tree prediction is the average of the training data within the region. Very cool. So there's so many ways in which statistics and probability gets tied in. We use a variety of probability models. I often just work with the priors and the postures and the likelihood functions and work with conditionals and joints and marginals, all different types of probabilities. And you can use different types of estimators like maximum likelihood estimators and so forth, ordinary least squares. And there's so many ways in which probability and statistics tie into our machine learning. Therefore, for robust use of probability and statistics, robust use of probability and statistics is a prerequisite for machine learning. I hope I've convinced people of the value of it. What is probability? How do we use probability? Well, when you think about it, probability is central to how we make decisions in the presence of uncertainty. Anybody here like dealing with uncertainty in their own lives? You know what's really funny is I deal with probability and uncertainty every day, but I don't like it in my own life, but I still have to use it to make decisions. Well, at work, what can I do? If I know the probability that a well will be successful, then that can help me support the decision of drilling the well. If I know the probability of there being a crack in a valve of a blowout preventer, given the fact that it's detected by some type of a X-ray scan or what, then that can be used. That conditional probability will support the replacement of the valve as preventative maintenance and safety. What is the probability of a seismic survey will find a reservoir? Well, that's decision analysis. That's how we support the decision to spend the money on the seismic survey. And what's the probability that a reservoir seal will fail? Well, this is central to anything around carbon capture and sequestration in the subsurface, understanding if we have long-term viability for storage of carbon. Most of our decisions involve uncertainty. What I tell my students is that we live with uncertainty because the subsurface is so sparsely sampled. We sample typically about 1 trillionth volumetrically of the subsurface. By quantifying probability, we can make better decisions. I hope I'm preaching to the choir, as we say down here in Texas, that we all appreciate this. Let's go back and think about what probability is. You got to go back to the original axioms from Kolmogorov. And there were 3 fundamental axioms when it came to probability as a metric, a measure. Probability of an event is a non-negative number. Now, if you do a probability calculation and your probability comes out as being negative, I hope you'll look outside to check to see if you destroyed the universe, because that's paradoxical. That can't happen. There's no negative probability. So probability of a outcome must be greater than or equal to 0. It can be 0. It can be impossible to happen. Unit measure, probability of the entire sample space is 1. We like to use the term omega. Omega on a Venn diagram represents all possibilities, all things that can happen. The probability of all possibilities is 1, and that makes sense. That's a good axiom. I like that one. Additivity of mutually exclusive events for unions, that's another one of the axioms that Kolmogorov came up with. The idea that the probability, and this is just simply a summation over all of the, or union summation over all of the possible things that can happen, A index I, is going to simply be the summation of the probability each one of them, given their mutually exclusive events. They don't occur at the same time. Probability of A1 or A2, 2 different mutually exclusive events is going to be just the summation of the two probabilities. These are the three fundamental axioms upon which Kolmogorov built a lot of ideas around probability. Now, given those axioms, and we're starting to think about probability, what are the different perspectives we can take in order to calculate, to work with probability, to communicate probability? There are three distinct methods. There's a fourth, but I have trouble distinguishing it from the third. And so we'll just stick with three here. Long-term frequencies. This is the idea that probability is a ratio of outcomes. Actually, what's very interesting is that the long-term frequency perspective is tied to the experiment. In other words, you run an experiment, you have repeated observations, replicates, as we say in statistics, and then you use the proportion of times that something happened over the total number of times you ran the experiment as a probability. This is long-term frequencies. Spoiler alert, this is fundamental to the frequentist approach. Physical tendencies, propensities is a very interesting idea. So if I had a coin, and I had one, I lost my coin. Oh, here we go. I think this is an American dollar coin. I didn't even know we had these. If I took this coin and I flipped it, now I'm not going to do it because I'm pretty sure I'm uncoordinated to the point where I'm going to hit myself in the face with it. But if I flipped it and let it land on my desk really nicely, and it was to fall, I think we'd all agree that just understanding the coin, the physics, the actual properties of the coin, we could probably figure out 50-50. We could probably even figure out at some point that there's a 1 out of 6,000 chance for the coin to land on its edge. Did you know that? For a balanced coin, it's about 1 out of 6,000. I think somebody correct me if I'm wrong, but that actually is a thing. We could do that all by knowledge of the system. We could work out the probabilities of the events or outcomes. Turns out that there's many systems in this world for which physical knowledge is just not enough. It's too complicated. Our systems often are way too complicated. The third methodology is degree of belief. Now, I hope that you're not disturbed by the term belief. Don't worry, we're defining it a little bit better as we go along. But it comes down to it's reflecting our certainty about the result. Now, this is interesting. This number 3 takes us outside of the experiment. It allows for our experience, our knowledge to come into play. It's very flexible. We can assign probability to anything, updating with new information as we go along. Anybody who's listening, I bet many of you realize that this is going to be related to Bayesian perspective for probability. So let's go ahead. We've defined the 3 fundamental perspectives for probability. 2 of them are directly linked to frequentist and Bayesian approaches, and we are now free to define frequentist and Bayesian. 2 slides, and then we'll proceed. Frequentist approach, measure of likelihood that an event will occur for random experiments in well-defined settings, such as coin tosses, such as a closed system where you can run an experiment, look at the outcome from it. The mathematics, the probability of A occurring, denoted by shorthand, P of A, is just the limit as n number of experimental trials goes large enough. Now, this is getting away from the issue around the false belief in the law of small numbers, which is very dangerous, in which this is the ratio of n, the number of occurrences of A divided by the number of all occurrences. You see the omega term right there. This is the frequentist approach. If you have enough experiments, enough replicates, you can take the ratio and you can call that a probability. Frequentists do this all over the place. Some people are critical of frequentist approach, will say you cannot use that outside of the experiment. I am not as strict in my perspective of frequentist approaches. I do believe, and we've talked about this before, you can use assumptions of stationarity. You can use these ratios elsewhere too. So an example is the probability of drilling a dry hole for the next well, or encountering sandstone, or whatever it might be. You just go ahead and you look at the percentage of times, or the ratio of times that occurred, and you assign that as a probability. That's frequentist. The Bayesian approach is quite different. I've shown right here Bayes' theorem adjusted into the usual formulation. The Bayesian approach to probability is interpreted as a reasonable likelihood representing our state of knowledge, or as a quantification of personal belief. Specifically, we will deal with establishing a prior, this P of A. We will update with the likelihood, right here, the PB given A, a conditional probability. We will standardize it by the evidence term, P of B, and that will get us to what we need, the posture. This is the P of A given B. This is the overall approach. Let me just put some words back on it. P of A will be our prior. That's our information, our knowledge, our degree of belief before we gathered new information. PB given A is the new information. And P of A given B is now our updated posture probability given our prior belief and our new information. Now, this is a very powerful perspective. It allows us to do all kinds of great things as far as integrating new information, multiple information sources. I want to make a couple of comments here. I'll probably emphasize this later on. The prior, one of the biggest issues people have, and has anyone here ever seen it before, where you use the new data to inform the prior. You ever seen anybody do that? They go into a subsurface setting and they're supposedly updating with well data using just geophysical information for the prior, but they're in fact using some of the well information to inform the prior. You're not allowed to double dip. You can't take information that's being used in the likelihood and use it in the prior. Professor Pyrcz at Stanford University, we work in very similar areas, does great work in this, and has suggested that we need a much broader prior than we usually work with. Anybody ever seen the Birdbeak plot, where you look at a project over time, and you look at how the uncertainty changes as you collect new information? Typically, you'll see something like this occur where uncertainty decreases over project time and information, and then it jumps up again. That's usually caused by this issue of assuming too narrow of a prior when we start. And then we realize later on when we collect new data, we were too narrow in what could happen. Yeah. Okay, so let's introduce the concept of Venn diagrams. I don't think I even need to introduce this. I'm sure many of us have worked with Venn diagrams before, but just in case, the idea of a Venn diagram, very powerful. Omega and a box. The box is everything that can happen. Then you can have circles, you can have squares. Some of my students get a little freaked out when I use a square or a different shape. Doesn't matter. The whole idea is that this is representing the size of A and the size of B represent the relative likelihood of each. I think we can all see B is probably about twice or a little bit more likely than A. Now, given this Venn diagram right here, what do you think is the probability of A and B occurring together? Anybody? I'm testing the lag. Let's see how much lag there is. 0, Bo, you nailed it. Perfect. I'm going to guess there's a couple seconds of lag. So I think we're understanding the general concept of a Venn diagram. Very useful. Actually, as a challenge question, let me just give you a challenge question and see if anyone can come up with it in the chat window. This is kind of fun. If you had independence between A and B, what would that look like in a Venn diagram? Now remember, independence doesn't mean A and B don't occur together. They can occur together. Just I'm curious if anyone can get this, because this is a tough one. I challenge my students with it. A and B are independent. Tell me what the Venn diagram would look like. Fun, eh? Okay. So we can do a lot of interpretation on Venn diagrams. I'm going to let that sit. Don't worry. And if the suspense is killing you, at the end of this discussion, I'll tell you, I'll draw it for you if you like. Let's talk about complementary events. Why are we doing this? Everything I explain right now is so we can show some cool examples. A complement. If A is an event, A complement is A does not occur. So if I have a Venn diagram and this is A, this is omega, I'll tell you, you got to draw the box. A lot of students in my class forget to draw the box. And then A complement is everything that is not A. If A is sand and the reservoir at a certain location, A complement could be shale, could be something else carbonaceous or any other volcanics. It could be anything else. The mutual exclusive events will look like this. If the events do not occur together, that means that A intersection, that symbol is intersection with B, is equal to a null set. They never occur at the same time. You draw it in a Venn diagram as they do not overlap at all. And Bo, you nailed it. You got it. You knew that. Let's talk about conditional probabilities. Actually, there's a lot you can do with conditional probabilities. And if anybody has ever worked with naive Bayes, it's all driven by this. It's really, really cool. Okay, let's talk about conditional probabilities. The probability of B given A occurred is the probability B given A. This vertical line, you read it as given. Now, how do you calculate that? Let me show you the equation and then I'll explain it on a Venn diagram. The probability of B given A has occurred or is occurring is equal to the joint, the probability of A intersection with B. You can read this as A and B occurring, divided by the probability of A. Now, if I try to explain this, I think the best way to do it is to look at a Venn diagram. Everybody sees this Venn diagram. That's A, that's B, that's A and B occurring together. That's the overlap. Now, I said A occurred or is occurring given A. So now what we have to do is we take the omega and we shrink our universe because I told you A occurred. So I take that entire box and I shrink it down. And when I do that, this is my universe. That's all that can happen because A occurred. Now, if I want to calculate the probability of B given A, I just have to take the ratio of A and B divided by A. That's exactly what this equation is. That right there is the definition of conditional probability explained by looking at a Venn diagram and thinking it through. There are many times I use conditional probabilities. I'll use it to communicate in business. I'll do conditional expectation. I'll do conditional P10, P90. It's very, very powerful. Anybody ever used a violin plot? They're full of conditional probabilities. Very useful. All right, so now I've explained conditional probabilities. We talked a lot about Venn diagrams. This is a good group. So let's go ahead and let's challenge ourselves. I want you to take a look at case one right here. We got A and B Venn diagram. We got case two right here. Please calculate for each one of these cases and put in the chat window whenever you're ready, the probability of A given B, probability of B given A for both of them. I'm going to give you about a minute to think it out, to think it through, okay? If you have a question, feel free to ask by chat window or by Q&A. I'll give you a couple more seconds for case one. Anybody got it? What's the probability of A given B for case one? Now I put the equation up here. So I have provided you a little reference to help out. Anybody by chat window. Sometimes my students wonder how long I'm going to wait. All right, all right, all right. Now, Rodrigo, you can give me a number. Like, this is awesome. You got the definition. You're exactly right with the definition. But you could actually simplify that further to actually giving me the probability. You might be shocked by that. But in these cases, you don't have to get out a measurement tool like a planometer or something and try to figure out the area of these circles. You don't. You can actually give me a number for these. Anybody got it? And I do, Rodrigo, I do appreciate them. 0, 0, 0. Okay, excellent. 0. Hugo, thank you very much. Probability of A given B, given their mutually exclusive events, the joint is equal to 0. Hugo, Edgar, you nailed it. Perfect. It's 0 divided by the probability of A, and that's going to be simply equal to 0. So both of these is equal to 0. Now case 2. This is more complicated. Hugo, Edgar, I want to challenge you and others. Let's see if we can get this. What's the probability of A given B? Let's try that one first. This is the case. Anybody shrinking their universe? Probability of A given B. Avi, how much lag do we have? Okay. All right. Let me see. Anybody got it? Let's do this one together. Oh, here we go, here we go. I have an n divided by 1. Now, once again, you can give this to me, given the problem you have here. Okay, all right, let's see what we got here. We just got an answer, Geetha. I hope I'm pronouncing your name correctly. I apologize if I've got that wrong. Let's walk through it, and you nailed it, you got it. The probability of A given B, you shrink your universe to B. If you put your fingers like up to the screen and do this. If you shrink your universe around B, what's the probability of A? 100%, because when the universe is shrunk down to B, all cases have A also. You see that? A is all of this area. Okay, everybody see that? Isn't that cool? Conditional probabilities are very powerful. We can use them all over the place. Probability of B given A. Anybody? Geetha? Edgar? Bo? Anyone got it? Let's walk through this. We're going to walk through this. Probability of B given A. Okay, now let's shrink our universe. Where are we going to shrink it? We're going to shrink our universe to A. A has occurred. Now the probability of B given A has occurred is simply going to be the probability of B divided by, yes, nailed it, Geetha, you nailed it. Perfect. Probability of B divided by probability of A. Everybody see that? We could solve all of these. This is a wonderful example. I know they're a little almost pathological, a little bit more challenging for conditional probabilities, but if you can solve these, you can solve many problems with conditional probability. I want to show you something else. This is very powerful. We're going to use this to solve Bayesian problems. It turns out, you remember that closure? It feels like it was just 10 minutes ago that we stated it. You remember? Probability of A plus the probability of A complement is equal to 1. It turns out that that closure has a conditional partner. Closure with conditional probabilities is right here. The probability of A given B plus the probability of A complement given B is equal to 1. Do you see that? You see why that works? The way it works is this. If you say it's given B, you shrink your universe to B as occurred. Now, if we shrink our universe to B occurring, we shrink it around B, there's only two things that can happen, A or not A. And so the summation of these two conditional probabilities is equal to 1. Does everybody see that? There are so many good cases where we can use this to solve problems. I'll show you one right away. Now, there should be no surprise. Is anybody surprised by the idea that I can reverse the A's and the B's and I get the same thing? That I have another formulation of conditional probability closure? Not a big deal. The thing we have to remember is that the A's and B's are just labels, right? They're just labels for events. We can reverse them, not a big deal. And in that case, we're shrinking our universe to A, and we have either B occurred or we have not B occurred. And if we sum those up, we get 100%. Okay, very cool. This was a lot of fun. These concepts can be very powerful. Now we're ready. Now, and everything we've done up until now has been pretty straightforward, kind of axioms and probability. Let's go ahead and build this into something really cool. Take the definition of conditional probability. Everybody sees it. Probability of B given A is equal to the probability of A and B divided by probability of A. Now, we can define that. We can actually understand that directly from the Venn diagram. I showed it to you. Can we all accept that this is an axiomatic definition? We can figure it out. We can just see it. It turns out that you can take this term right here in the denominator and put it in the left-hand side. Everybody agrees that the fundamental concepts of algebra still work with probability. We can go ahead and take that and put it over here. If you do that, you now have what's known as the multiplication rule, the general form. Now, there's no assumptions for this. We don't have to assume independence, Gaussianity, or something else. Nope. This is fundamental probability axioms, works in all generality. Probability of B and A is equal to the probability of A given B times the probability of B. Now, remember what we said before, we can reverse A and B. Anytime we can reverse them. So let's go ahead and do that. Reverse A and B, we reverse it, you have to be consistent. How you reverse on the left side, you have to reverse the same way on the right side. If you do that, can we all agree both of these are valid? Okay, so we got two forms of the multiplication rule. No assumptions required. Now, would you all agree that the probability of B and A should be equal to the probability of A and B? Is there any reason to believe that the ordering of the events matters? Not in this case. No, we're just talking about A and B occurring. So this also we can state as axiomatic. Now, if you can trust that, and if we know this is valid, we can take both of these and substitute the right-hand sides into each one of these, and we make this. This is the combination of two product rules with this simple symmetric, joint symmetric relation. If we do that, we get the probability of A given B times probability of B is equal to the probability of B given A times the probability of A. This is Bayes' theorem. Now, any questions, comments by chat window? We all together? Derivation of Bayes' rule, no problem. All right. Now, this gets us to more deeper discussion about Bayes' theorem and Bayesian statistics. It turns out that probabilities based on degree of belief are essential. This approach is needed in scientific endeavor. In fact, let me give you a very simple example. I love this example from the first edition, Savai. There's a new edition just came out, I believe, Bayesian tutorial book. 1996 from Zavia. The question was posed in the first unit, first chapter, what is the mass of Jupiter? Now, a frequentist would say, let's measure the mass of many gas giants. And then we'll use that as a distribution, a PDF. We can calculate the expectation, all of its moments, and we can start to say something about mass of Jupiter by using that information. The frequentist approach, multiple experiments. Now, you have to remember, 1992 was the first discovery of a confirmed exoplanet. I know nowadays we feel all modern, we got thousands of them. We could do this now, but back then we didn't have that information. A Bayesian approach allows us to use prior information and update with any available new information. And that prior could be broad. And then we could use whatever type of indirect measures with their level of quality to try to update and refine to a posterior. In this case, mass of Jupiter, as Savia suggested, we needed a Bayesian perspective. We could not use the frequentist approach. Now we could. We have replicates, but we couldn't back then. Bayesian statistical approach, probabilities based on state of knowledge, degree of belief in an event. We utilize assessment of a prior to data collection. We must have a prior model before we have the new data. We update with new information as it's available, and we can solve many probability problems. You cannot use you could not use frequentist approaches. I don't want to show a bias here, but I use both. I'm not saying I'm just a Bayesian statistician. Now, What's very interesting here is it turns out that you can do this sequentially. You could have a prior, get new information, update to a posterior, then that's your new prior going forward, get new information, update, and you could cycle. That's valid as long as we don't double dip. Bayesian credibility intervals provide a more intuitive measure of uncertainty than the frequentist confidence intervals. We could make a lot of comments around that. I do really very much appreciate that. That's an advanced concept. I recommend you take a look at credibility intervals from the Bayesian perspective. Okay, let's talk about this again. Make an easy adjustment to the Bayes theorem from before, and we get the common form. I showed this before. I have already stated that this is the posterior, the likelihood function, the prior, and the evidence terms. Let's make a couple of comments. One of the great things about the Bayesian approach is you can go from the probability, conditional probability inversion in a way. You can go from the probability of B given A to a probability of A given B. There's many classes of problems for which we have one and not the other, and it's very useful. I'll show you examples. Prior should have no information from the likelihood. This is a common issue. Many people mess this up. It's hard not to, because when you formulate the prior, you often do have the data in front of you and you use it. It's hard not to. Evidence term usually is just a standardization. I'm going to show you how we calculate it. It turns out it's hard to calculate. It can be hard, but it in fact is we can standardize, and I'll show you how we do that. Bayes' theorem, this is the common terminology right here. A common usage goes like this. Let me change A and B to other terms or labels to make it clear. We could be calculating the probability of a model given new data. We would use the probability of the model. That's the prior. The probability of the new data given the model. That's the likelihood term. That's effectively like the probability of the data given the model you already had. And the probability of the new data is the evidence term. Now look at this. This is really cool. Notice that the evidence term has nothing to do with your model. That's interesting. Very, very interesting. We'll take advantage of that. There is a symmetry, of course, as everything we talked about. A and B are just labels. So we can do the probability of A given B. We can do probability of B given A. Just be consistent. There's an alternative form for the evidence term. You know, the probability of A is usually very difficult to calculate, as I mentioned. And so what we commonly do is we use an expanded form. Now, it might be hard to believe, but this is easier to calculate than this is in many cases. In other words, this right here, if we break it down, probability of A given B times probability of B, that's the multiplication rule. And we already know that's equal to the probability of A and B. This is the probability of A and B complement, the joint. And I hope everyone can see that the probability of A and B plus the probability of A and not B, that's closure. Well, we can understand immediately that that's equal to the probability of A. All right, so we can go ahead and we can substitute. We'll do that. What type of problems are we going to use to solve with this formulation? Well, this is a very common set of problems. It goes like this. Event A could be somebody has a disease. And I know this is a difficult example. I mean, no insensitivity. It's just a very good teaching tool as far as getting it in our heads. Probability is somebody has a disease. Now, there's also this. Event B is the probability that they test positive for the disease. Can everybody see that these are two different things? Which is more important to us? The probability of B or the probability of A occurring or B occurring? Can we all agree that we're much more interested in whether or not the person has the disease versus the detection? Now we can take that to more engineering problems, the probability of fault compartmentalization in groundwater, oil and gas, whatever it might be, versus the event B being the geologist. The geoscientist says they think there's a fault, detection. Probability of valve will fail given B, probability that the test will indicate a positive. These events are different from each other. How do we characterize this or summarize? This is a general class of problems that go like this. We want to calculate the probability something is happening given it looks like it's happening. The thing is happening given we have a detection of it happening. And this is the formulation of Bayes' theorem right here behind it. Very, very powerful. You can take these parts of the equation, we can take it apart and start to make some interesting observations. If you look at this right here is the probability something looks like it's happening given something is happening. That's the correct detection rate. The probability something is happening is the occurrence rate, and the joint is the proportion overall of both it looks like it's happening and it is happening. That's a true positive. And if you look at this complement right here, that is going to be the false positive. And so this becomes very logical. The probability of something happening, given it looks like it's happening, is the true positive joint divided by the true positive joint plus the false positive joint right here. And this is all cases for which you would detect it happening. Very, very cool. This is going to be very, very useful. Let's take a problem right here. Let's go ahead and solve this together. Prior information at a site suggests a channel feature exists. Good news. That means good reservoir structure. At a location with a probability of 60%, we decide to investigate with seismic information. The seismic survey can show that the channel is present with 90% probability if it really is present. If not present, with 70% probability if it is not really present. So in other words, seismic's going to say it's not there if it's not there with a 70% probability, that conditional probability. Seismic will say it's there, given it is there, 90% probability. Okay, let's put some labels. Always got to put a label. A, the feature is present, the channel structure. B, seismic shows it, the detection of the feature. A complement, B complement are the opposites. Not a big deal. This is what we know. Probability of A. We have an overall probability of a channel structure is 60%. That is a prior. That came from other type of information, geologic intuition, knowledge about the setting, analogous reservoirs, other sources. The probability of the channel, 60%. Probability that the seismic shows the feature, given the feature is there. A means there is a channel there. We said it right here, 90%. You see that? Probability B given A, 90%. Probability of B complement, false, the detection saying, nope, it's not there in seismic. Given it's not there, A complement is 70%, 0.7. Okay, now let's go ahead and use Bayes' theorem to solve the problem. What is the probability that the feature is present given seismic says it's present? Okay, we need to populate this equation. What are we missing? We need to calculate the probability of A complement and the probability B given A complement. Can anybody help me with that? Anyone? Probability of A complement, we can just use the closure relation. 1 minus the probability of A, 0.4. Bo, you got it. Nailed it. Thank you very much. I do appreciate it. Edgar too. And I do apologize. I'm sure there's a little bit of lag since we're broadcasting. Thank you. You nailed it. And I understood. You got it. And the probability B given A complement, we can use the other closure relationship. 1 minus B complement given A complement, 0.3. We do all that. We can populate the equation and we get back the probability of A, the feature, the channel, given the seismic detects the channel, 82%. Let me ask you, is it worthwhile to shoot the seismic? Is the seismic helping us? What do you think? How do we assess that? First of all, 80% probability given seismic indicates it pretty high. We work in many companies where we use 80% confidence intervals and so forth. That's a pretty good indicator. The other thing is look at the prior, the probability of the channel before we shot seismic, 0.6. If we can increase the certainty, 0.6 to 0.82, that's good. Let's make a couple of comments about linear regression, and then we're going to show an example just very quickly in code and finish up. Thank you very much, Bo, for the feedback, and I appreciate Edgar, you jumping in on the questions. Let's take a linear regression, super easy, super simple. If anybody hasn't done linear regression in Bo, I'm simply talking about some type of reflection seismic survey in which we've done inversion to try to get rock properties at a location in the subsurface. That was my idea of a seismic survey without diving into the details of seismic inversion or analysis of amplitudes versus offsets and all the things we can do with seismic, or 4D, which is awesome. No, but just simply saying seismic. Thank you both for the question. I appreciate that. Now, if you haven't done a linear regression, I'll tell you what, you can open up right now. You can open up SciPy stats. You can use linear regress. You can give a vector with the X, a vector with the Y, and you can do linear regression. You get the slope, the intercept, the R value, the R squared value, the probability as far as the slope term and its hypothesis test, the standard error in the slope. You could get everything one step, boom, you've got it. Now, what's very interesting, linear regression does have a lot of devilish details. I'm not going to spend time right now because I am kind of running short in time, but there's a lot of really interesting aspects to linear regression. The optimization of a loss function is one of them. A lot of people don't realize I created an interactive display that actually does linear regression for different norms. Loss functions, this one right here should have a squared term right there. It disappeared, but I've shown it for other terms with other norms, which is very powerful. There's a lot of assumptions to linear regression. Error-free data, the predictor features, the X's have no error. Let me just show you what that looks like. In other words, when we fit a linear regression model, we'll allow for there to be error in Y, but there is no error in X. These dots are not allowed to move side to side. That's very interesting. There's a lot of things we could talk about as far as limitations. We can even calculate confidence intervals with linear regression. This is the slope term, the B1 term. This is the intercept term from linear regression. And we can calculate with analytical expressions in the student t distribution their uncertainties. We can prove them up by doing bootstrap, which is really, really cool. Okay, so we can calculate the uncertainties, confidence intervals for the model. We can also calculate the prediction interval, which is the uncertainty in the prediction from the model. That's even more uncertain than the model itself because there was error in the model in the first place, and the model itself is uncertain too. Okay, now remember we talked about Bayesian statistics, probabilities based on degree of belief, priors updating the posteriors. You know what's fascinating? We can solve the entire linear regression problem from the perspective of a Bayesian model. This is fascinating, in fact. What we do now is we need to go ahead and calculate Y as a model of X and slope terms. If people familiar with matrix math will recognize that the B transform, the beta transform is just the coefficients for all the X values being applied specifically to the specific X values. So this is X1 times B1, X2 times B2, and so forth. And this right here is the error term. Now, what's the beautiful thing about the Bayesian approach for linear regression? We don't just solve for the ordinary least squares, the best estimate. We, in fact, pose the entire probability with an assumption of an uncertainty distribution, in this case, a Gaussian distribution. Now, if we do that, we can actually solve for these beta coefficients, the slope terms for the linear regression and the constant term, using this Bayesian formulation. Now, what we have is we have a prior. So we can give what our initial guess or belief, or using a previous information, what do we think the model will be? Then what we do is the likelihood term is fascinating. It's the probability of the data given the model right here. So the data, the X and Ys, the density and porosities that I showed before. And then we divide by this normalizing constant right here, probability of the data. And if we do that, we can get a posterior, the probability distribution for the model parameters given the data. Very, very powerful. Now, let me just comment. The prior, that's your initial inference of the model parameters. It can be naive. You can put in a uniform distribution, a very wide Gaussian distribution, and say, I don't know. Now, what's very interesting, if you do that, the answer will converge on the frequentist approach without the prior as far as its measure of expectation for the parameter distributions. You can also have expert knowledge integrated here. We have likelihood. That comes from the data. It's the data-driven component. Now, just like I said before, if the data tells you very little, And then the prior is going to dictate everything. And we have the evidence term, which is, and I show it here, it's a marginalization. It simply is an integration over all of the possible model parameters to get to get the closure correct, so all the probabilities sum to 1. That ensures closure, and the posterior is going to update from prior to likelihood to be able to get an updated model. Very, very fascinating. Okay, so let me go ahead. I'm going to just open this up and introduce to you a very simple workflow. This workflow is available to you on our learning management system. It's a nice, well-documented workflow where we can walk through and do linear regression, Bayesian, and frequentist approaches. I'll just show it to you and we'll finish up for today. Let me show it to you right here. We're going to use open source packages in Python. Now, if you haven't done Jupyter Python before, I do apologize. With these webinars, we don't have enough time to kind of dive in and talk details about Jupyter and how we work it. We'll load up the world's brilliance as far as open source packages in standard Python. Now what we'll do is we'll open up PyMC3. It is a wonderful package for doing Bayesian modeling, sampling Bayesian modeling. We check and we make sure its version is modern. I don't need to update my machine. We'll go ahead and we'll load up a data set. The data set we're going to work with is grain size versus porosity. I showed this example in the notes, I believe. I may not have, but it's another simple example of one input, grain size, one output, porosity. Let's go ahead and visualize the data. That's it right there. Simple problem. Everybody can see it's a very simple example. Now, like I showed you before, SciPy stats. I can go ahead and just run linear regression with the X and the Y data, simple, and I get the model parameters, I get the R-squared values and so forth. Useful for a linear model, in fact. And this is the model right here. And given that model, I can project it onto the data. And this is my model fit, my ordinary least squares fit, minimizing the squared error at the data, training data. Now I can do all kinds of confidence intervals right here. These are frequentist confidence intervals, assuming the student t distribution. I can go ahead and calculate that the lower and upper bounds with regard to model parameters like the slope term. And I can use that right here. I can go ahead. Oh, this is the confidence interval at the 95% significance level. And up here, these in fact were the upper and lower bound for a testing. And we see we can calculate the t statistic, compare it to what we have right here. And we can say that we can reject the null hypothesis. This slope is significant. Okay, so we did a hypothesis test. How do you do Bayesian linear regression? Well, this is fascinating. I'm not going to run this because it does take about 2 minutes on my computer, and I don't want to use that time right now. We can formulate the distributions, the prior distributions of the intercept, the slope, and the error term. We can then show our model right here. We can then sample from it using Markov chain Monte Carlo simulation, which is awesome. And what this does, we'll do 4 separate chains, we'll sample, and then we can look at the statistics. The problem is that Bayesian calculation is too difficult to calculate for most continuous response features. And so what we have to do is we have to sample the problem and look at the sample set. Okay, if we do that, we can look at the summary statistics right here. This is our Bayesian fit, but it also provides us with these credibility intervals. And so we get the entire distribution of uncertainty of the intercept, the slope, and the sigma terms. Now, if we had enough time to run this, I ran it for a naive case. I would adjust the prior. Just go ahead, check out this code on the learning management system, change the prior and see how that changes the posterior updated. Okay, I'm going to leave it right here. I think this is a very interesting workflow. I welcome people to try it out. I hope this overall discussion of frequentist and Bayesian probability machine learning was useful to you. Send me an email if you have feedback or comments. All right, Avi, are you still here with us?
Hey, Michael, still here. Can you hear me?
Avi, I don't hear you.
Can you hear me?
Fantastic. Hugo, thank you very much for the feedback. I do appreciate that. Geetha, thank you very much for your feedback. Nailed it. I think you're one of our experts on conditional probabilities. Both the slide decks are available on the learning management system. Check in with Avi. Avi can help there. Okay, All right. Avi, we don't hear you, but thank you. Now, folks, I like to hang out and talk, but I do need to run and see a company right now. Professors are always trying to get money, right? So I'm going to go see a company right now, but I'm happy to discuss anytime. All right. Everybody stay safe. Thanks,
everyone.
Avi. Appreciate your help today.
Absolutely, Michael.